In this video, we're going to have a look at the graphing of the sine and the cosine functions. So at the very start of trigonometry, we told you that trig is used on triangles. So to analyze the side lengths and their relationship with the angle theta. So this was really great for the current content that we had looked at, but going forward, we're going to have a different perspective on trigonometry. So we're going to stop looking at them as ratios, but rather we're going to start looking at the trigonometric functions as actual functions. So what does that mean? We'll consider if we had, say, function t, and the definition of function t was sine of t. So what we'd like to do is, if we graph this, we'd like to see what the function sine t would actually look like. To help us understand the behavior of these functions, so the sine t and cosine t, what we're going to do is go back and have a look at the unit circle. So recall in the unit circle, we had a point, or we had a line, and we drew the line starting from the origin, and we draw it out such that the line was of a length 1, and then we fanned the line across an angle of 0 radians to 2 pi radians. And what we found is that when we move this line across that range, this point here, the extremity of the line draws a circle as such. Now, what we want to do is, for any point along this circle, for any angle here, any angle of theta, we want to know the vertical, so this red line, and the horizontal displacement from the origin. And because this length of the line here, the orange one, is a length of 1, what we know is that this red line, the length of this red line can be described by sine of the angle, so sine of the angle theta, and this horizontal component can be explained, or the length of this green line can be explained as cosine of the angle. And for an angle between 0 radians, so 0 radians down here and pi on 2 radians, notice the behavior of the red line. So as the sine component increases, this cosine component decreases. Furthermore, the sine component starts at a value of 0 and it grows to a value of 1. Now, rather than picking a few random points to plot into Desmos to see the behavior of, or to see the curvature of the sine function, what I propose is we use the exact values that we got from our unit circle over here, and we're going to use the exact values. So we're going to say for 0 radians or 0 degrees, we'll go a sine of 0. For pi on 6 radians, we'll go half pi on 4, root 2 on 2, pi on 3, root 3 on 2, and pi on 2, 1. So if I plot those all into Desmos over here, notice what we get. So I'll plot them in, and I'll split this up actually. So we'll say we've got a range of 0 radians to 2 pi, and then I'll split it into the quadrants as well to make it easier to understand. So quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And what we can see is the output of the sine function, it starts off at 0 and at pi over 2. So in the first quadrant, it finishes up at 1. So drawing that, what we can see is we get this funky looking function here. So notice that in the lower values of the angle, it grows quite aggressively, but as the angle approaches pi on 2, it starts to taper off in its aggressiveness. Now let's go back to the unit circle and let's increase the value of the angle. And notice when we hit pi on 2, the sine component is 1, and then it starts to decrease and go back down to 0. So when it hits radian, or when it hits an angle of pi radians, it goes back to 0. So what do you think this part will look like when we graph quadrant 2? Well, putting in the points, notice that the behavior of the function is reflected. So quadrant 1 and quadrant 2 for the sine function is reflected. Okay, let's go back to the unit circle and we'll increase our range once again. And notice when we go past pi radians, the sine, or the vertical component, the vertical displacement, goes negative because we're below the x-axis. And it goes towards -1. So when we hit an angle of 3 pi over 2, we hit a vertical displacement of -1. Then when we pass into the fourth quadrant, we're still negative, but we're heading towards 0 again. So going back over to this plot here, what do you think it's going to look like? So in quadrant 3 and quadrant 4, we're going to expect negative. So quadrant 3, we're getting more negative. And then in quadrant 4, we're going back to the positives. So graphing these two, have a look at that. So in quadrant 3 and quadrant 4, the sine is negative. Now what's more is that quadrant 3 and quadrant 4, they mirror one another about x equals 3 pi on 2. Similarly, quadrant 3 and 4, they mirror quadrant 1 and 2 about the x-axis. So this, or what we see here, this is the general behavior of the sine function. Now what about the cosine function? What would that look like? Turning off the points for the sine function, and then turning off our sine function here, let's have a think about what our cosine function will do. So I'm not going to plot any more points, but rather based on what we saw the sine function look like, and based on this unit circle here, let's consider what do we think cosine will look like. So going back to quadrant 1, when we have an angle of 0, our horizontal displacement, so this green line here, represented by the cosine function, has an output of 1. And as we increase and move towards pi on 2, notice how our horizontal displacement is changing. So we started at 1, and then we're moving towards pi on 2. So at pi on 2, we hit a value of 0. Pi on 2, we hit a value of 0. So graphing cosine, what we're going to see is, this guy. So we're starting at 1. We're starting at 1, and then we're going down to 0. So quadrant 1. Now quadrant 2. Notice what the cosine looks like in quadrant 2. So it moves to the left-hand side of the y-axis and starts becoming negative. And it reaches its most negative at pi, where it equals -1. So going back over here, consider what that's going to look like. So over in quadrant 1 we're positive, now we're going to go negative. So it's going to keep going downwards. Now quadrants 3 and quadrants 4, we'll do those ones together. So as we're in quadrant 3, it starts off at -1 and then it starts moving towards 0 again. So this section here, notice it's approaching a horizontal displacement of 0. Then when we hit quadrant 4, we go back into the positives and it starts moving back to 1. So the function over here, quadrant 3, remember we were negative, And then quadrant 4, we go positive. So we expect this guy to start going back to 0. So when we hit x equals root or 3 pi on 2, we're back at 0. And then remember the horizontal, so the length of this green line here, it's positive in quadrant 4. So what we're going to expect is this to be positive here. Neat. So comparing this cosine graph to this sine graph, consider what we have. The shape is very similar, but the only difference is the shift about the x-axis. So notice when sine is starting out, it starts at 0, but when cosine starts out, it starts at 1. When cosine hits 1, when sine hits 1, the cosine is at 0, and when sine is at 0 again, cosine is at -1. So at every stage, the sine function, or you could say the cosine function, is 90 degrees ahead of the sine function, or you could say that the cosine function is pi on 2 radians ahead of the sine function. Now, another tool we can use to see the behavior of these functions is this tool here. So if I turn on the cosine, or the sine, sorry, and we can see as the unit circle changes, so the horizontal and the vertical components, as these change, it's going to graph. A nice graph for us over here. So I'll turn on sine and cosine at the same time, and we can see how it sketches it out. So notice the changing vertical and horizontal displacements and the corresponding sine and cosine functions being plotted out. So the final component to talk about here is consider, as this point is swept around the full range of the circle, so 0 radians to 2 pi, when it hits 0, or when it hits 2 pi radians, it simply goes back and starts canting upwards again. So what we would find is, if I pause it there, so 68, in fact I won't pause it at 68, we'll go to 90. 90 degrees would be the same as saying 360 degrees plus 90, and this value would be exactly the same, or we could say 2 pi radians plus pi on 2 radians would still give the same value up here. So the functions themselves are always going to keep repeating this general shape over and over and over again. Now if we go to this Desmos function, notice that if we play it, look what happens with the sine function as we keep going over a different range of angles. So what we can see is between 2 pi there, we've got one rotation or one period of the function, and if we increase it to 2, so 2 times 2 pi radians, so 4 pi radians, the function itself repeats itself twice over. So this sort of behavior, we call it periodic, and both the sine and the cosine function behave in this manner, such that if I plot it over an infinite range, this is what we'd expect to see. And again, this is reflected because notice that the circle, if I can bring it back up, the circle just keeps going round and around and around and around. So it's always repeated. So in summary, what we found today is that we can express the sine and the cosine ratios not as ratios, but rather as functions. And when expressed as functions, this is what they look like. Both of them have a range of 0 to 2 pi radians, and both of them have a domain of -1 to 1 on the y-axis. Comparing them two together, then what we can see is that the cosine function is pi on 2 radians ahead of the sine function, and the general shape is roughly the same. In the next video, we'll have a look at what we can do to change the shape of the sine and the cosine functions ever so slightly.